Okay, so in this lecture here, basically we're going to begin the introduction to the geometric modular. First, let's summarize what we've done so far, basically in terms of the convergence properties of sequences in the ordinary metric space. Now, in the setting of the geometric space, um, a sequence x sub n in X is said to converge to X in X if in the large n limit and m limit, the gene distance between the n term of the sequence, the m term of the sequence, and x is equal to 0. The sequence is said to be a Cauchy sequence if in the large n limit, m limit, and l limit, the gene distance between the n term of the sequence, the m term of the sequence, and the l term of the sequence is 0. The metric space, the geometric space is said to be complete if every Cauchy sequence in it converges to a point in X. And then finally, the Banach fixed point theorem says that if the pair X gene sub D is basically a geometric space which is complete, and T is a self-map, which is a contraction, which basically means the gene distance between T of X, T of Y, and T of Z is less than or equal to C times the gene distance between X, Y, and Z for all X, Y, and Z in X, where C is a positive constant less than 1. Then T has a unique fixed point. That basically means that T has exactly one fixed point. Okay, so now let us look at the G-modular metric space. So we consider a function of the form G of lambda x, y, z, where lambda is basically a positive real number, and x, y, and z are basically some points in the set X. So the only difference between the G distance and then the G modular metric is basically the G modular metric is a more flexible version of the G metric because all the variables are not restricted to the particular set. The variables can be defined on different sets compared to the G metric where all the variables are restricted to the same set. So a function G of the form G of lambda x, y, and z is said to be a geometric modular if the following axioms are satisfied. Note, we write the function of the form G lambda x, y, and z to be G of x, y, z sub lambda. Okay, so a G modular metric satisfies the following properties. For any x, y, and z in X, G of x, y, and z sub lambda is equal to 0 if and only if x is equal to y is equal to z. Okay. B. The geometric modular is symmetric with respect to the variables x, y, and z. That is, G of x, y, z sub lambda is equal to G of x, z, y sub lambda, and so on, for all lambda greater than 0 and x, y, and z in X. And then third, the geometric modular satisfies the so-called triangle inequality. That is, G of x, y, z sub lambda plus mu plus sigma is less than or equal to G of x, y, z prime sub lambda plus G of x, z prime, z sub mu plus G of z prime, y, z sub sigma for all lambda, mu, sigma greater than 0 and x, y, z in X.